Okay, section 2.3 in our text is about the derivative function. So let's take a review of the derivative at a point. I'm going to look at the simple example f of x equals x squared and calculate the derivative at x equals 1. We know from what we've been doing in class that if we want to calculate f prime of 1, we start by writing the limit as h goes to 0, f of 1 plus h minus f of 1 divided by h. And then we have to take this 1 plus h and substitute it into the formula for f, which gives us 1 plus h quantity squared. We substitute 1 into the formula for f, we get 1 squared, which is 1. And then we do a little bit of algebra here and try to simplify. If we expand 1 plus h squared, we get 1 plus 2h plus h squared. And then we subtract that 1 over here. So the 1's cancel. And we can factor an h out of what results. If we factor h out of the numerator, we get 2 plus h. And we can cancel those h's. And this is something that frequently happens. We breathe a sigh of relief. And now we know at this stage we can simply plug 0 in for h. And if we do so, we get 2. This means the slope of f, or the slope of the tangent line to f, at x equals 1 is 2. This is what we call the derivative at a point. And of course, we could replicate all of these calculations just by replacing 1 with a 2, or the 1 with a 3, or so on and so forth. And we could construct a table of values. For example, if I wanted the derivative at 1, I would get a 2. If I wanted the derivative at minus 1, I could replicate the preceding calculations and get minus 2, and so on and so forth. And what we have here is a table that represents a function. So instead of looking at the derivative at a particular value, be it 1, negative 1, 2, negative 2, 0, we're going to look at the derivative function, the derivative at an arbitrary value of x. So we write f prime of x. We take the formula that we used above, and instead of using a 1, or instead of using a 2, or instead of using a 3, we simply use the variable x. So we have the f prime of x is the limit as h goes to 0, f of x plus h minus f of x divided by h. Again, the only difference now is that we have a variable x instead of a particular number. Now let's see if we can find the formula for the derivative function in this particular case. So here's f of x equals x squared, and the derivative function definition from the previous page is that f prime of x is the limit as h goes to 0, f of x plus h minus f of x, all divided by h. Now, just like in the preceding page, when we took 1 plus h and substituted it for x squared. We do the same sort of thing. Now this is a little bit more difficult because we're taking x plus h, something that involves x, and we're substituting it into the formula here, which is why I like to put a little box around this x. We're going to take x plus h and we're going to substitute it in the box. And if we do so, we get x plus h quantity squared. The formula for f of x is just x squared, so we're going to subtract that. And we go through our calculations just like we did before. We expand this, we get x squared plus 2xh plus h squared. We're going to subtract our x squareds here. Those cancel. And we're left with the limit as h goes to 0 of 2xh plus h squared. We factor in h out of that. And if we do so, we get 2x plus h. Now, we're not taking the limit as x approaches a particular value. We're taking the limit as h approaches 0. So if we simply plug 0 in for h here, we get 2x. Now we have a formula that allows us to calculate the derivative at any given value of x. We don't have to go through the same limit process for 1 or 2 or 3. For example, f prime of f, instead of using the limit formula, I could just plug 5 into this formula and I get 10. Likewise, if I want f prime of negative 7, I can plug negative 7 in and I get 2x. So even though there's a little extra work here, because there's an x floating around, The benefit is that now I can calculate f prime at any value. Now we're going to take a look at the graphs of these two functions, and that's really the primary issue of concern in the next few minutes. So here's a graph of f of x equals x squared. You'll notice that it's a parabola opening up. And here's the graph of the derivative function that we obtained on the previous page. F prime of x is 2x. It's a line with slope, well, slope 2, unlike this line. Now take a close look at what's happening on the parabola. If I draw a tangent line here, 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 anywhere over on this portion of the graph, the slope of that tangent line is positive. In other words, the slope of f is positive. That means the derivative function at this x value, at that x value, everywhere is going to be positive. In other words, the graph of the derivative is positive, or it's above the horizontal axis. Likewise, if I look at this graph over here, the slope of f there is negative, the slope of f there is negative, the slope of f there is negative, or in other words, f prime is negative at every x value over here. We see that in the graph of 2x. It's below the horizontal axis, or in other words, it's negative. And if I look at the vertex of the parabola, if I draw a tangent line to the vertex, it has slope 0. So f prime evaluated at 0 is 0, which is why this crosses the axis right there. And there are other patterns as well. For example, if I draw a tangent line there, its slope is positive. Its slope here is more positive, and so on and so forth, which is why the derivative is going up. Over here, if I draw a tangent line there, it's negative slope. Tangent line there is negative slope, but less negative. So we see the derivative values becoming less negative. And it's for these reasons that sometimes I like to refer to f prime as the slope of f function. It records the slope of f. So whenever the slope of f is positive, like in the case of the parabola, the graph of f prime is positive, or in other words, it's above the x-axis. Wherever the slope of f is negative, the graph of f prime, which is the slope of f function, is negative. In other words, below the x-axis. And when the slope of f is 0, like on the vertex there, the graph of f prime crosses the x-axis. So what we're going to be doing in the next few minutes is trying to build upon those properties and start with the graph of a function whose formula we don't have and simply graph the derivative function. We'll start with a simple example. F of x equals the absolute value of x minus 4. This is the graph of the absolute values function, which is V-shaped, and we've shifted it over so the vertex is at 4, 0. Now, if I look at 1, x equals 1, the derivative at x equals 1 is negative 1, because the slope of the function at 1 is negative 1. The slope of the function, f, at 2 is negative 1, and the slope of f at 3 is negative 1. So the slope of f at 1, which is the derivative, f prime of 1 is negative 1, and so on and so forth. So at every x value between 0 and 4, the graph of f prime of x is going to be below, and the slope is always going to be negative 1. So here's negative 1. The derivative graph is going to be negative 1 everywhere there. And again, that's because the derivative records the slope of f. The slope of f here is negative 1, the slope of f there is negative 1, and so on and so forth. I'm using the fact that we have a rise of negative 4. We go down 4 and we go over 4. That's where the slope of negative 1 is coming from. And I'm going to stop the graph right around here and come back to this point in a moment. Likewise, if I look at f at 5, the slope of f at 5 is 1. The slope of f at 6 is 1. The slope of f at 7 is 1. At every x value between 4 and 8, except 4, the slope of f is 1. So that means the derivative will look like this for values in between. Now what's happening at 4 itself? At 4 there's a sharp corner. And what that means is at a sharp corner, I really can't draw a tangent line. It's going to swivel like this. At a sharp corner, the derivative is undefined. The derivative is defined just a little bit to the left of 4, because a little bit to the left of 4, the slope is -1. No matter how close I am to 4 on the right, as long as I'm not equal to 4, the slope is +1. So that means we actually have holes here, and the graph of the derivative function is what we see in red. Let's take a look at a slightly different example. A little more complicated. Okay, so this function is basically piecewise linear. If we look at what's happening between 0 and 2, the slope of f, which is f prime, everywhere between 0 and 2 is 0. F prime of 1 is the slope of the tangent line at 1, which is 0. F prime at 1.5, which is the slope of f at 1.5 is 0. Everywhere here. But then there's a corner at 2, so this is going to be hollow. Now, everywhere between 2 and 4, we go over 2 and we go up 2. So at 3, the slope of f is 1. The derivative at 3 is 1. At 3.5, the slope is equal to 1. That means the derivative at 3.5 is 1. At 2.5, the slope of f, which is the derivative, is equal to 1. So everywhere between 2 and 4, the derivative graph, which is in red, is going to be equal to 1. Again, there's a corner here, a cusp, and there is one here, so this is going to be, whoopsie, that should be hollow. Sorry about that, that should be hollow. In fact, that it shouldn't be there. Now, between 4 and 5, at every point on the graph of f, the slope is, well, we go down 3 and we go over 1. So that means that f prime of 4.5 would be -3. F prime of 4.25 would be -3. So our derivative graph is going to be living down here at -3. And this is hollow because at 4, the derivative is undefined. Now what happens at 5? At 5, there's a big gap in the function. We can't draw a tangent line when there's a big gap like that. I mean, where do we draw it? The function isn't even defined, so there's going to be a hole there as well. Finally, if we look at what's happening between 5 and 8, we go over 3 and up 2. That means we have a slope of 2/3 everywhere between x equals 5 and x equals 8. So I'm going to go down over here to about negative, this is -1, so -2/3 would be right around there somewhere. And this is going to be hollow. The graph ends at 8, so we'll make that hollow, and likewise we'll make this hollow back here as well. So again, the derivative is the slope of f. The slope of f is 0. The derivative is 0. Everywhere in here, the slope of f is 1. The derivative is equal to 1. Everywhere in here, the slope of f is equal to -3, which means the derivative values are -3. Everywhere in here, the slope of f is 2/3 because we went over 3 and up 2. So the derivative graph is down at 2/3. Let's take a look at one last example, which is a little bit more complicated insofar as the graph curves a little bit. Again, there's no formula for the graph. Let's take a look at the easy parts first. Over here, everywhere between 5 and 8, the slope everywhere here is 0. The slope of f is 0, which means the derivative graph will be 0 everywhere between the function, we'll put a hole there. And because of this corner or cusp at 5, that has to be a hole. Slope of f is 0, derivative is 0, or on the x-axis. Now, right here at 3, the slope of the tangent line would be 0. So f prime of 3 is 0. So the derivative graph crosses there. So what I'm doing first is I'm looking at where the derivative is constant, or in other words, where the graph of f might have straight line pieces. Then I'm looking where the derivative is 0, in other words, where the graph of f is flat. Now let's take a look at what's happening over here. These pieces are a little bit more challenging. Over here, the graph of f is increasing. Another way to say that is that the slope of the tangent line there is positive. The slope of the tangent line there is positive. The slope of the tangent line there is positive. Because the slope of f is positive, f prime between 0 and 3 will have to be above the x-axis. Now, we don't really know how far above the x-axis it is, but we can estimate a couple points because this graph has grid lines. So let's go over to, let's say, about 1.5. I'm going over to 1.5, or maybe something like 1 instead. Let's go over to 1. Now, take a look at my ruler. It's kind of hard to guesstimate, but let's say I look what's happening up here. If I look at this portion, I go over 1 unit, and I go up, let's just call that a half. Okay, so I go over 1, up a half, so that's a slope of 1/2. That means that f prime of 1 is roughly a half. So I'll draw a point at 1/2 right there. If we look at f prime, let's say at a quarter, it's going to be greater than f prime at 1. F prime of 1 is here. F prime of a half is here. F prime of a quarter is about here. Those slopes are all larger. So what's going to happen is that the function f prime is going to have to decrease because the slopes are large and they're getting smaller as x increases. Let's go really close to the origin here. Really close to the origin. And let's draw a tangent line to the graph. Tangent line to the graph like that. It almost looks to me like maybe the tangent line is going over 1 and up 2. So that would be a slope of 2. So maybe the derivative near the origin is about 2. That means that we have a few points here. Let's just connect those few points to get a curve. Okay? Now this is very qualitative. We know that f prime has to be above the axis because f has a positive slope throughout. The slope of f is getting smaller as I move from left to right, which means the derivative values should be getting smaller as I move from left to right. The derivative is 0 here, which means the slope of f is 0 here, which means the derivative is there. Let's do this portion over here finally. We know that f is decreasing. The slope of f at each point here is negative. That means f prime is going to be below the axis. We also know that the derivative is going to be, taking a look at this, we know the derivative is equal to 0 there, and we know that the slope of f is negative and becoming more negative. Slope is 0, slightly negative, more negative, more negative, more negative, more negative, more negative, and maybe it's most negative just a little bit to the left of 5. So let's draw a tangent line there, just a little bit to the left of 5, and see if we can estimate its slope. Well, it looks to me, if I go a little bit, just a little bit to the left of 5, it's a very rough estimate, but it looks to me like I went over 1 and down 1, 2, 3, 4 units. So a little bit to the left of 5, the slope is about -4. So I'll go down here to -4 and maybe put a point right there. This has to be hollow at, 5, because the derivative is undefined there because of the cusp. Now the derivative is the slope, and the slope is negative and becoming more negative, which means that the derivative graph is going to be below and be going more below. Now again, this is very qualitative. Whether the graph goes down like that or whether it goes down like that is not important. What is important is that the graph is below and that the graph of the derivative is becoming more negative. Okay, so I'll see you in class. The goal of this video is that you're able to actually graph the derivative when we have simple sections where the graph is piecewise linear, or maybe a few curves.